Hello everybody, welcome back to our channel. In this episode we're going to be solving a Physics 7B final exam type problem. This problem has momentum, rotational inertia, and angular momentum concepts. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe, it really helps a lot. Feel free to pause the video if you need to, this is kind of a long problem, but let's just go ahead and breeze through it. So to defend himself against 7B students angry about their grades, Joe makes up this rotating gun turret as shown in the picture below. The gun turret consists of two 500 kilograms each cannons attached to a metal disc. The entire thing is held in place by a bolt through the center of the disc. This bolt allows the disc to rotate without friction. The disc has a mass of 1,000 kilograms and a radius of 2 meters, and the center of mass of each cannon is located 1.75 meters from the center of the disc. To test his turret, Joe loads each cannon with a 5 kilogram cannonball and then fires them at the same time. This process takes 0.1 seconds to accelerate the cannonballs, and Cannonball 1 leaves Cannon 1 with a speed of 80 meters per second. Cannonball 2 leaves Cannon 2 at a speed of only 30 meters per second. Both cannonballs are launched directly to the right. We have a bunch of questions that we have to answer here, but let's just go ahead and read the first two, which we're gonna do first, and then we can come back and read the next ones. So the first two questions are, what is the force exerted by the cannonball on Cannon 1? And then what is the force exerted by Cannonball 2 on Cannon 2? We need to be careful about this, so let's just go ahead. So as you can see, I have everything here written down in my notes. I have the picture, I have the masses, final velocities of both the cannonballs, and then this equation is going to be useful for part 4, so let's just go ahead and ignore that for a second. So, what is the force exerted by Cannonball 1 on Cannon 1? So this is force by ball on Cannon 1, which is not the same as the force by the cannon on the ball. However, because at this point we know Newton's third law, we know that whatever force the cannon puts on the cannonball, it's equal but opposite that the force that the ball puts on the cannon itself. If you wanna see this through a momentum chart, we could do that. So let's just go ahead and just think about this. Ignore this spinning disc and just think about the ball and the cannon. So if you do a momentum chart, so both of them start at 0 because the ball is not moving inside the cannon and the cannon is not moving at all, so totally 0. Momentum is conserved because there is no mention of any friction or anything, so this is 0 and this is 0 because this row has to add up. The cannonball ends up having some certain momentum to the right, and that basically means that the cannon needs to have a certain momentum to the left in order for this to add up to 0, and these delta p's have to add up to 0 as well. Now, this delta p would be the impulse of the ball, and we can actually calculate it because we do have a final velocity, an initial velocity, and the mass of the ball. Now, this delta p in this direction to the right is equal in magnitude that this delta p going to the left. Delta p is equal to F net delta t. Now, for the cannon, delta p is equal to force by ball on cannon times delta t. So basically, whatever force this one feels to the right, this one feels to the left. So if we calculate delta p for the cannonball, which is the information that we have at the moment, then we can just invert the sign, and that would be the force that the other one is feeling as well, because delta T is exactly the same for both of them. It's 0.1 seconds. 0.1 seconds. So let's go ahead and figure this out. So force by ball on cannon 1 ball would be the inverse of the change in momentum for the ball divided by delta T. And the force by ball on cannon 2, using the same logic, has to be the opposite of the change in impulse from ball 2 divided by delta T. So the thing that we have to do now is figure out this delta P, and then delta T is just 0.1, and that will basically give us our answer. So let's just go ahead and do this. Delta P is equal to, okay, so this is negative just because there's a negative here. Delta P is equal to mass times delta V. And delta V is final minus initial. However, there is no initial. So final minus initial, initial being 0, means B final. Same goes over here. Like this. Remember, this negative sign is important because if we don't put the negative sign, we would be calculating force by cannon on ball. But we want force by ball on cannon per the instructions. So this is why we need to flip the sign. Okay, so let's just go ahead and grab our calculator. So force by ball on cannon 1 is equal to negative, which means it's gonna go to the left, which makes sense. If this one is pushed this way, we need the other way. So let's see. So mass of the cannonball is 5 kilograms. The final velocity of this one is 80. And delta T for both cannonballs is 0.1. This gives us a force of 4,000 newtons. And this negative sign means to the left. Final answer of part A on the final exam. So using the same procedure, we just need mass of the ball, which is 5. However, the second one was only going 30 meters per second. So that gives us a force of 1,500 newtons, again with a negative sign, and this means to the left. So that will be magnitude and direction for part A and part B of this final exam problem. So let's just go ahead and read part C. So part C says, what is the net torque, magnitude and direction on the gun turret as a result of firing the 2 cannons? You may assume the cannons remain attached to the disc so that you may treat the cannons and disc as one object. Okay, so for part C, we need to figure out what is the net torque. So let's just go ahead and draw an extended force diagram because we already have 2 forces here. So let me just pick another color. So we have a force in this direction to the left, and this force is 4,000 newtons in magnitude, and we have another force over here. This force is 1,500 newtons in magnitude. This is the axis of rotation of this problem. This is the pivot point. So if we want to balance, we don't want to balance our torque. We just want to find our net torque. Well, let's just use our equation. Torque is equal to RF sine of an angle. And the net torque is just equal to the addition of all of the torques. In this case, we only have two forces acting on this problem, this upper one and this lower one, and both of them generate torques because they are not being applied at the pivot point and they are not parallel to the moment arm. So let's just go ahead and calculate both of the torques. So I'm just gonna call them torque 1 and torque 2, 1 being for cannon 1, 2 being for cannon 2. So for cannon 1, this distance is 1.75 meters because there's symmetry here in the problem. So this distance is the same as this distance. So this is 1.75 meters times force, which is 4,000. And sine of the angle, in this case, both of these cannons make a 90 degree, both of these forces, make a 90 degree angle with R. So sine of this angle is equal to 1, so I'm just going to ignore it. And the direction of this torque, if you use your right hand rule, will be out of the page. Out of the page is positive in standard convention, so this number is a plus. Now for the other cannon that we have right here, this cannon with this force, if you use your right hand rule, then you're gonna see that this torque actually goes into the page. So this torque is actually negative. R is equal to 1.75 as well, and we need to use the appropriate force, so we need to use the 1500. So if I add this together to find the net torque, I'm gonna find that the net torque is equal to, oh, there we go. So this is negative 4375. The units are newtons meters, and this is a positive number, so if positive is out of the page, direction is out of page. Final answer for part C. Now let's see the next part of the problem. The next part of the problem, it says for part 4, assuming that each cannon acts like a point mass, what is the total moment of inertia of Joe's gun turret? Alright, the disc and the two cannons. Recall that the moment of inertia of a disc rotating around its center is given by I disc is equal to 1/2 mr squared. Okay, so this goes for a disc. So we need to figure out, let me just go ahead, what is the total moment of inertia of the system. So the total moment of inertia of any system is the addition of the individual parts of the system. So in this case, we basically have three different objects. We have a disc and we have two cannons. So I total would be the I of the disc plus cannon 1 plus cannon 2. I of the disc is given with this equation, so it should be very straightforward to just copy this. So I of a disc is 1/2 mass of the disc, because this is for the disc, so the mass of the disc is 1000. And R of the disc would be the radius of the disc, so the total radius of the disc is equal to 2. For the two cannons, this problem is asking us to assume that they act like a point mass. So I of a point mass is the one that we know, which is just the sum of mr squared. So for this cannon, we have to use mass of the cannon, which is 500, R, which is 1.75 squared, and then the other cannon will be exactly the same because this problem has symmetry, so I'm just going to go ahead and copy that twice. Okay, so at this point we can just add up everything. So let's see, so we have 1/2 times 8,000 times 2 squared plus 500, 1.75 squared plus 500 times 1.75 squared, and I get 5,062.5, and the units are mass radius squared, so that would be kilograms meters squared. Final answer. There we go. So the only thing that we needed to be careful about, because a lot of people did this, when we give you an equation, a lot of people just jump and just use the equation, but we needed to be mindful. The instructions were asking us for the total moment of inertia of the system, not just the disk. So not adding the cannons is obviously a mistake. So now the final question is, what is a turret's final rotational velocity? Okay, so for the final question, we need to find turret or disk. Now, as you can see over here from what we calculated, there is a net torque on our system. Now, because delta L is equal to net torque times delta T, if there is a net torque, that means that there will be a change in angular momentum. So if the turret was stationary after the cannonballs fire, it will start rotating. And we need to figure out what the final angular velocity of this disk is. Now, we already have that delta T is 0.1, and we already know that this is the net torque of the system. So I think that this is going to be straightforward. Let's just go ahead and do that. Delta L is also moment of inertia times delta in angular velocity, delta T. Angular velocity is final minus initial. However, we don't have an initial angular velocity. So because omega initial is equal to 0, then this basically gets transformed into just the final angular velocity. So if I solve for this, then this is net torque times delta T divided by I. In terms of numbers, net torque is 4375, delta T is 0.1, and I is equal to 5062.5. So if I use my calculator, that should give me a final answer. 4375 times 0.1 divided by 5062.5. There we go. So this is 0.086 radians per second, but we need to be careful. This is a final exam problem. They're always tricky. Angular velocity is a vector. They did not ask me for angular speed. They asked me for angular velocity, and a complete answer is for any vector is magnitude and direction. We know the magnitude already. The only thing that we have to figure out is the direction, and for that we're going to use our right-hand rule. If we use our right-hand rule, you'll see that this goes out of the page like this, because the net torque, well, you can do this in several ways. You know that this goes out of the page because your net torque is going out of the page, and then these two things are the only ones that have any direction to them. So this direction has to be the same as this direction. Another thing that you could do is that because this force is greater, you can just use your right hand rule like this, and that will give you out of the page. So at this point there are like 3 different ways that you can figure out that it has to be out of the page. So whatever one you decide you are the most comfortable with will work. If you would like me to make a video about just using the right hand rule, no numbers, no anything, just a bunch of scenarios and just using right hand rule, do leave a like and a comment, and I'm happy to work that out if that's something that's, you know, gonna be interesting for students. But yeah, most important thing here is just not forget that a complete vector answer is magnitude and direction. Magnitude, direction, magnitude, direction. So this basically finishes the problem. I really hope that this was useful to you guys. If it was, please leave a like and subscribe to our channel. It really helps a lot. I'll see you guys in the next video.